So now we will be starting from nomenclature of elements with atomic numbers greater than 100. इसके पहले हम लोग देखें कि periodic table कैसे बना, मतलब starting पे law of triads आया, फिर Newland's law of octaves आया, after that Mendeleev's का periodic table भी आया, क्योंकि काफी हद तक modern periodic table से मैच करता था. फिर उसके बाद जब हम लोगों को एक प्लॉट बनाया रूट अंडर न्यू अगेंस्ट atomic number, तो वो straight line आ रहा था, but root under mu against atomic weight straight line नहीं आ रहा था. इसकी वजह से जो atomic weight के हिसाब से अरेंज किए हुए थे एलिमेंट्स को, उसको हटा करके atomic number के हिसाब से अरेंज कर दिया और उसको modern periodic law बोलते हैं. So the naming of new elements had been traditionally the privilege of the discoverer. मतलब कि जो एलिमेंट्स जिस साइंटिस्ट ने या फिर बनाया है उसके नाम से उस एलिमेंट का नेमिंग किया जाता था. And the suggested name was ratified by the IUPAC. In recent years, this has led to some controversy. So the new elements with high atomic number are so unstable that only minute quantities, sometimes only a few atoms of them are obtained. So their synthesis and characterization therefore require highly sophisticated, costly equipment and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting the reliable data on the new elements, at times get tempted to claim for its discovery. For example, both American and Soviet scientists claim credit for the discovering elements 104. The Americans named it Rutherfordium, whereas Soviets named it Kershatovium. To avoid such controversies, IUPAC has made recommendation that until a new element's discovery is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element using the numerical roots for 0 and number 1 to 9. So these are shown in table 3.4. Until and unless you discover something and prove its chemical properties and physical properties, everything, you will not be credited for its discovery. So IUPAC has suggested that before the complete identification of any element is done, so its name will be given according to table 3.4, which is recommended by IUPAC. So digit 0 name will be nil and abbreviated as N. Okay, so it will be according to the atomic weight. So if the atomic weight is 104, so it will be UNQ, or you can say it as nil quad. So this is the way of naming it. So you can see in table 3.5 the nomenclature of elements with atomic number above 100. 101 is given by, as I told you, abbreviated from the symbolic form, we can see, and this is the name according to the IUPAC nomenclature. Okay, and this is the IUPAC official name. So these are the scientists who have actually discovered it. But before getting all the physical insights and chemical insights of that element, so it is always initially named according to this IUPAC table 3.4. So these are shown in table 3.4, and the roots are put together in order of digits, as I told you. So which make up the atomic number, and IUM is added at the end. So IUM is basically given for the metal. So the IUPAC names for the elements with Z above 100 is shown in table 3.5. So there's a new element first gets a temporary name with symbols consisting of 3 letters. Later, permanent name and symbols are given by both of IUPAC representatives from each country. Like who has really discovered it will be given according to the vote. Okay. The permanent name might reflect the country in which the element was discovered or pay tribute to a Nobel scientist who has discovered the element. So as of now, elements with atomic numbers up to 118 has been discovered. So official names of elements with atomic numbers 113, 115, 117, and 118 are yet to be announced by IUPAC. Okay. So for these, they are used the IUPAC nomenclature that we discussed in table 3.4 and 3.5. So problem 3.1 is that what would be the IUPAC name and symbol for the element with atomic number 120? So you can see 1 to 0 is what? 1 is un, 2 is by, 0 is nil, and lastly you need to add IUM. Okay, and for when you write it in simple form, then you don't have to add IUM at the end. It will be UBN or unbinilium. So electronic configuration of elements and the periodic table. So it is very, very relevant because we all know, we have studied in previous last pages that this whole atomic periodic table is basically, it reflects the similarity in the electronic configuration in a group. So we need to know the electronic configuration of the elements and periodic table, and since it is arranged and classified into groups and periods, so you don't need to really memorize all the electronic configuration of all the 118 elements separately, because these are grouped already. So if you only know one of them in a group, then you know everyone in the group. So in the preceding unit, we have learned that an electron in an atom is characterized by a set of 4 quantum numbers with groups, right? Principal quantum number is n, which defines the main energy shell, which is known as a level, which is known as a shell. We have also studied about the filling of electrons into different subshells, also referred to as orbitals. So shells is given by the principal quantum number, subshell, that is the S, P, D, F, is given by the azimuthal quantum number, and the distribution of electrons into these orbitals of an atom is called its electronic configuration. So electronic configuration is nothing but the distribution of electrons into the orbitals. So an element's location in the periodic table reflects the quantum numbers. So these 4 quantum numbers, if you know the values for these 4 quantum numbers, then you can easily tell about the electronic configuration of that element. So since all the elements has a unique electronic configuration, hence all the elements has unique 4 quantum numbers. None of the quantum numbers, there is no 2 elements that has same 4 quantum numbers. So basically the quantum numbers reflects the location of the element in the periodic table. We can say it like this. So in this section, we will observe a direct connection between the electronic configuration of the elements and the long form of the periodic table. So as I already told you, so periodic table and the electronic configuration has a lot of similarities in between them. So periodic table is made in such a way that you don't need to remember all the electronic configuration. Only you know the electronic configuration of any one element in the whole group. You know the electronic configuration of all the elements in that group. So the first one that we are going to study is the electronic configuration periods. And also after that, the step heading is the group-wise electronic configuration. So there are 2 types of ways in which the periodic table is arranged, group and periods. So we are going to discuss the electronic configuration period-wise and also electronic configuration group-wise. So starting with the period-wise, so the period indicates the value n for the outermost of the valence shell. Okay. So what is the value n? It is a principal quantum number. So this quantum number, principal quantum numbers, is basically period indicates the principal quantum number of that element. So in other words, successive periods in the periodic table is associated with the filling of the next higher principal energy level, n equals 1, 2, etc. So it can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. So we know that in one single orbital, you can fit 2 electrons having opposite spins. And if you don't understand this, then we will be discussing it. Okay, so yes, we will hear. So it can be readily seen that the number of elements in each period is twice the number of orbitals available in the energy level in that is being filled. So the first period, that is n equals to 1, starts with the filling of the lowest level, that is 1s, okay, and therefore has 2 elements, that is hydrogen and helium. So 1s, and after 1s, what you have? So we all know how to fill the orbitals. So the that is already taught in chapter number 1, and It is given in chapter number 1 how the electrons are filled. So it is 1s, then 2s, 2p, 3s, 3p, 3d. So this is the way of filling up the orbitals. So the first period, so the only one, so n equals to 1 is only 1s. So and in s there is how much orbitals? So in 1, when n is equals to 1, then L can be how much? So L is the azimuthal quantum number, and L can only be 1. Okay, so in that, and in one orbital we all know that you can fill maximum of 2 electrons having opposite spins, because if you put 2 electrons having same spin, then it will, the quantum number associated with spin, that is the spin quantum number, will be same, which we don't want. Okay, so for n equals to 1, how many elements should be possible? So how many number of electrons you can fill in that particular principal quantum number orbital? So it is only 2, 1s1 and 1s2. So period number 1 has to have only 2 elements. So it is hydrogen and helium, we know that. So when the first shell K is completed, the second period N equals to 2 starts with lithium, and the third electron enters the 2s orbital. So the next element, beryllium, has 4 electrons and has the electronic configuration of this. So it is quite straightforward, right? So it is like 1s, then 2s, 2p, 3s, 3p, 3d, right? So, and we all know about the filling of the orbitals, and which the orbital which is lower in energy by the n plus L rule will be filled first. So we know this, right? So this is the filling of the orbitals. So this, for principal quantum number 1, only maximum 2 electrons can be filled, and for principal quantum number 2, maximum how many electrons can be filled? 2 for S and 6 for P. So maximum 6 you can fill in the second period. So second period will have, sorry, not 6, 8. So second period will have how many elements? It will be 8, right? So starting from the next element boron, the 2p orbitals are filled with electrons when the L shell is completed at neon. Thus, there are 8 elements in the second period. Okay. The third period, N equals to 3, begins at sodium, and added electrons enters the 3s. Successive filling of 3s and 3p orbitals give rise to the third period of 8 elements from sodium to Rp. Now you will have one question. I told you that we have, for the third period, how much? That is 3. So we have 3s. How many orbitals are possible for principal quantum number 3? So you will say that it is 3s, 3p, and 3d. Okay. How do you know that? So you know it as, for like third period, n equals to 3. So how many orbitals are possible? So L can be 0 to n minus 1. Right? So L can be 0, 1, and 2. So total 3 types of orbitals can be filled. So 0 stands for S, 1 stands for P, and 2 stands for D. So for principal quantum number 3, you will have these 3 orbitals. But that does not guarantee that all these 3 types of orbitals needs to be filled in period number 3 only. No, period number suggests the highest principal quantum number any element can have, and not whole of it. So this does not mean that in period number 3, you can fill how many electrons? 2, 6, and for D it is 10 electrons maximum you can fill because there are 5 orbitals in D. Because ml is the number of orbitals in subshells, right? So for S, it is only L is 0, so it is 0 only. So basically ml has minus L2 plus L number of orbitals. Okay. So ml for S, L will be 0, so it will be only minus 0 to 0 is nothing but 0. For P, that is L equals to 1, so you will have minus 1 to 1, that is minus 1, 0 and 1. So in this way 3, and in each orbital you can fill 2 electrons, so total 3 into 2, 6. So 6 elements, right? So this is the way of calculating it. So this does not guarantee that total 18 elements will be there in period number 3. No, this is not true. In period number 3, there is again 8 elements only. So this means that this 3D, and you know what is the energy. So energy of an orbital is given by the n plus L rule. So let us calculate the n plus L. So here n is 3 and L is 0. So 3. Here n is 3 and P is how much? 1. That is by n plus L rule, it has a value of 4. And here the value of 5. So this is the increasing value of the n plus L, and hence the increasing energy of the orbital. First, the lower energy of the orbital is filled, and simultaneously the higher orbitals are filled. But in the period number 3, the highest principal quantum number is 3. This does not guarantee that all the orbitals that has a principal quantum number 3 is filled in that period itself. Only 6 elements, only these two orbitals, that is the 3s and 3p, is filled. There is no elements, d block elements in the period number 3 is there. Okay, so the 3d orbitals are filled at zinc is equals to 30. So before that, if I will put here, now you may note, okay, successive filling of 3s and 3p orbitals gave rise to the third period of 8 elements with sodium to argon. The fourth period, that is n equals to 4, starts at potassium. So n equals to 4. So now, and also you will ask that why 3d is filled in the next period now and not in that period itself. So 4s will be the first orbital of the fourth period, right? So what is the n plus L of 4s? Calculate. It will be 4, right? 4 plus 0, 4. So whose orbital energy is higher? It is 3d that has higher orbital energy. So it will be filled after 4s, right? So this is the way you decide. So that is why 3d is present in the fourth period. So in the fourth period, this orbital needs to be filled after this 4s. And let us calculate 4p, right? So 4p is 5. So you will say that 4p, sorry, you will say that 4p also has 5 an energy number, and 3d also has 5. So which one will be filled after 4s? So it will be 3d will be filled after 4s because it has lower principal quantum number. So any two orbital that has same energy, so that orbital is filled first whose principal quantum number is lesser. So it will follow 4s, after that 3d, and after that 4p. So in period number 4, how many elements will be there? So 2, 10, 6, to total 18 elements are there in period number 4. Okay. So the fourth period starts with n equals to 4, and starts at potassium, and added electron fills up the 4s orbital. Now you may know that the 4p orbital is filled. Filling of 3d orbital becomes energetically favorable, and we come across the so-called 3D transition series of the elements. So this starts with scandium, Z equals to 21, which has the electronic configuration of 3d14s2. So the 3d orbitals are filled at zinc Z equals to 30 with electronic configuration of 3d10 4s2. Now 4p will be filled. So the fourth periods end with krypton with the filling of the 3p orbitals. I already told you how do you know which orbital will fill. first. Now, similarly, you will have the fifth period, which will have n equals to 5, beginning from Rupidium. Period number 5, that is similar to the fourth period and contains 40 transition series, starting at yttrium, z equals to 39. So this period ends at xenon with filling of the 4p orbital. So it is similar trend. If you do it in your notebook, you will get below. The sixth period, n equals to 6, contains 32 elements and successive electron enters at 6s, 4f, 5d, and 6p orbitals in order. Filling up of the 4f orbitals begins with cellurium and S and lutetium, which gives the 4f inner transition series, which is called the lanthanoids, which is not in the first table of the periodic table. It is next somewhere. So it's just start of the periodic table. So the seventh period, n equals to 7 and 7 is similar to the sixth period, the successive filling of the 7s, 5f, 6d, and 7p. It also has 18 elements, and most of the it contains most of the man-made radioactive elements. So this period will end at the element with atomic number 118, which will belong to the noble gas family. Now, filling up of the 5f orbitals after actinium, that is Z16, sorry, Z equals to 89, gives the 5f inner transition series known as the actinoid series. The 4f and the 5f inner transition series of the elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Okay. The next problem, 3.2, how would you justify the presence of 18 elements in the fifth period of the periodic table? So, let us study. So, n equals to 5. So, n equals to 0, 1, 2, and 3, right? So, the order in which the energy of the available orbitals 4d, 5s, and 5p, all of these increases as first 5s, after that 4d, and after that 5p. Okay, so here you will also have S, P, D, and F. So F will be 4F. So the total number of orbitals available are 9 because 4F is already written separately in the periodic table. So it is not counted as the period 5. Okay, so you don't consider 4F here. So there are 5S, 4D, and 5P orbitals. Total, how many orbitals are present? 1, 5, and 3, that is 9. And maximum number will be 9 to 80. Okay, so there is 18 elements in the fifth period. So this was, we were studying about the period-wise electronic configuration. Now we will be studying about the group-wise electronic configuration. So elements in the same vertical column or group have similar valence shell electronic configuration. You can see in the periodic table first. That will be very, very simple for you to understand. So this is the periodic table. Okay. So when you see the elements group wise, you see that its valence shell is very, very similar. So for example, for group 7, you have 3d5, 4s2. And for the next element in that particular group will have higher, just one plus one principal quantum number and it will be 4d5, 5s2. So if you remember the principal, if you remember the electronic configuration of the first element, then you automatically knows all the electronic configuration of that particular, of the elements of that particular group. So in group wise, the electronic configuration, the valence electrons, the valence shell, the filling of their valence shell is the same. So elements with the same vertical group, column or group have similar valence shell electronic configuration and the same number of electrons in the outer orbital and similar properties. And hence, because we know that the properties of an element is because of its some atomic particles, like where the electrons is, how many electrons, protons, neutrons are present in that particular atom. And if you have same number of electrons, similar trend of filling of the electron, so in the particular group. So this suggests that the elements in that particular group will have similar properties. So this is the basis of periodic table, right? For example, group 1 elements, that is the alkali metals, all have ns1 valence shell electronic configuration as shown below. So all of these, atomic number 3, 11, 19, 37, 55, 87, it is lithium, sodium, potassium, rubidium, cesium, and Fr. So the electronic configuration, you can write the whole electronic configuration, or you can just write the just previous noble gas and then start with the valence shell electrons. This is easy to remember. You just need to remember, memorize, or the noble gas configuration, and just you have to add the next electrons. That is the valence electrons. So these elements has valence electrons of 1. So group 1 elements has valence electrons of 1. So thus, it can be seen that properties of an element have periodic dependence upon its atomic number and not on atomic mass. So this also suggests the same thing. So this is what the modern periodic law suggests.